Welcome to Lesson 12G, Examples of Superposition in Potential Flow. In this lesson we show some examples and applications of superposition in potential or irrotational flow. I'll introduce the method of images and how we apply it to potential flows. We start with a flow called the Rankine half-body, where we superpose a uniform stream with speed v and a line source at the origin of strength v dot over L. Remember that superposition involves adding up stream function or velocity potential. In other words, we add component flows to generate a new, more involved flow. Note that we could add either velocity potential functions or stream functions. I chose to add stream functions. The superposed flow is the sum of the free stream flow, where psi equal Vy, and the line source at the origin, which has a stream function v dot over L over 2 pi times theta. But y equal r sine theta, so we'll put everything in cylindrical coordinates. So this is our stream function for this new, more involved flow. What can we do with this equation for psi? Well, for one thing, we can set psi to some constant and then plot r as a function of theta from this equation. In other words, we can plot streamlines, which are lines of constant psi, and we can calculate the velocity field everywhere. Once we know the velocity field, we can use Bernoulli to calculate the pressure field. I plugged this equation into Excel and drew a bunch of streamlines. So this is what the flow looks like. We call it a Rankine half-body because this body goes on forever to infinity. It never has a rear end, only a front end. Notice that it's symmetric top and bottom about the x-axis. And this dark green line is called the dividing streamline. It divides flow inside this body from flow outside this body. By the way, the flow is from left to right. So I'll put some arrows on some of these streamlines. I colored the streamlines inside the dividing streamline in red and those outside in blue. Since we have a source at the origin, imagine that this source is putting out red dye from the origin. All of that red dye is trapped within this dividing streamline. All the blue fluid is coming from upstream, and it goes around the dividing streamline. Far enough downstream, eventually we just have uniform flow again. At any point in the flow, I'll call this point A, we can add up the velocities vectorially. The free stream gives a velocity to the right. The streamlines for a source are rays, so the source contributes a velocity component in that direction, straight from out of the source to point A. We add these up vectorially to get the velocity vector at point A. What's nice about superposition and potential flow is that the velocities of the component flows, here the free stream and the source, simply add up vectorially. And you can see that this velocity vector is parallel to that local streamline. Now consider point B right at the nose. At B, the velocity is 0. B is called a stagnation point, since the flow is stagnant or zero speed. If we zoom in on that region around B, this is what we see inside the Rankine half-body and outside the Rankine half-body. At our point B, the speed at this point, due to the source moving to the left, exactly balances the speed of the free stream moving to the right. So these two velocity components cancel out and give us a zero flow at point B. Here's another useful application of potential flow. Any streamline in a potential flow can be thought of as a wall. If our dividing streamline is the wall, then this is flow over a Rankine half-body. But it's not really a wall. It's actually just another streamline. We're just imagining it to be a wall, and we imagine flow around it. But you can pick other streamlines and think of them as walls. For example, we can take the dividing streamline and the streamline that hits the stagnation point. If we think of that as our wall, then we have a model of flow over a hill. Or we can pick any other streamline, for example this one, and imagine it as a wall. Now we have flow over some more rounded hill. Let's do a little analysis of this Rankine half-body. This is our stream function, where we superpose the free stream and the source. Velocity component UR is 1 over r del psi del theta, which is 1 over r v r cosine theta, plus 1 over r v dot over L over 2 pi, since this grouping of terms is a constant multiplying theta. U theta is minus del psi del r, which gives minus v sine theta from this term. The r's cancel here, so I'll simplify, and u theta is minus v sine theta. We can find the location of the stagnation point which by definition is the point where the velocity is 0, so the two components of velocity have to be 0. From this equation, u theta equals 0 when theta is 0, pi, 2 pi, etc. Here u theta equals 0 when theta equal pi, or 180 degrees, which is to the left of the origin along the x-axis. Now we look at ur. ur equals 0 when negative v cosine theta is equal to 1 over 2 pi r v dot over L. But we know that theta has to be pi, and we know that cosine pi is negative 1. So ur is 0 when v equal 1 over 2 pi r v dot over L. Let's let this r equal a at the stagnation point, which is the distance from the origin to the stagnation point along the negative x-axis. Solving this equation for a equal v dot over L divided by 2 pi v. Thus, for any source strength and any free stream speed, we can calculate the distance from the origin to the stagnation point. Our second example is flow over a circular cylinder. Here we superpose a uniform stream and a doublet. So as we did with the previous problem, we add up the stream functions to generate our more complex flow. Uniform stream and the doublet. Again, we apply y equal r sine theta, and this is our equation for this more complicated flow in cylindrical coordinates. Remember that we can add an arbitrary constant to psi and it doesn't change the flow at all. I say here for convenience, and with hindsight, we set psi equals 0 at r equal a. A will be a special streamline that is a circle of radius a. Now we set r equal a in our equation for the stream function, and we get this, where we've also set psi equals 0. And thus we have an expression for the doublet strength that gives us a circle of radius a for some given free stream speed v infinity. Then our final expression for psi is given here. I plotted streamlines. I used non-dimensional variables, x star equal x over a and y star equal y over a. That way this plot is identical for any potential flow over a circular cylinder, and this radius is 1 in non-dimensional units. We also non-dimensionalized psi. As we did with the previous problem, we can calculate ur and u theta from the given equations for psi in cylindrical coordinates. You can see the textbook for more details. On the cylinder, r equal a, or non-dimensionally r star equal 1, we get ur equals 0 and u theta equal minus 2 v infinity sine theta. These are the velocity components on the wall of the cylinder. I put wall in quotes because in potential flow this is really not a wall, it's actually just a streamline. In fact, we have flow inside this circle because of the doublet, and those streamlines look something like this. No longer circles, but rather flattened kind of circles that fit within this circle of radius a, or radius 1 non-dimensionally. We're imagining that this circle is a wall, and we have the velocity components now along that wall. To get the pressure field, we use our most beloved Bernoulli equation. Ignoring gravity, Bernoulli is p plus 1/2 rho v squared equal p infinity plus 1/2 rho v infinity squared, where infinity is the free stream conditions far upstream. From this we generate a pressure coefficient, which is a non-dimensional way of expressing pressure. From our velocity field, v squared is 4v infinity squared sine squared theta. And when we plug that into here, we find that Cp is 1 minus 4 sine squared beta. Angle beta is defined along the wall from the front stagnation point. This flow is symmetric right and left, and there's also a rear stagnation point, and theta is defined counterclockwise from that rear stagnation point. Beta is the preferred angle for aerodynamics. Now that we have both the velocities and the pressure along the body, we can analyze. By nature of the sine function, the speed is 0 at the stagnation point and keeps increasing to a maximum at 90 degrees and then decreases again to 0 at the rear stagnation point. It's also symmetric top and bottom. I label the front and rear stagnation points. If I draw v infinity to scale, it turns out that v at the top is 2v infinity at beta equal 90 degrees. Mathematically, u theta is minus 2v infinity, but u theta is defined as positive counterclockwise, and here it's the opposite direction. The maximum speed in the flow on the outside of this cylinder is at the top, and it's equal to 2v infinity, and since it's symmetric, v bottom is also 2v infinity. I'll also sketch the pressure distribution along the cylinder. By Bernoulli, since the speed is 0 at the stagnation point, the pressure is highest, and when V is highest, the pressure is lowest, and I sketched the pressure at some other points. I note here that P equal P infinity out in the free stream, and we have maximum pressure at the two stagnation points. Notice that P is symmetric, both front and back, or fore and aft, and top and bottom. Top and bottom we might have thought, but front and back, that means that there's no drag on this cylinder. It turns out, in fact, that drag equals 0 on any non-lifting body in an irrotational or potential flow. This is called D'Alembert's paradox. I plot the pressure coefficient as a function of beta. The blue curve is our potential flow analysis, and we see that it's symmetric front and back. By the way, at the free stream pressure, Cp is 0. Cp starts at 1 at the stagnation point, dips to -3 at 90 degrees, and then back up to 0 at the rear stagnation point. Because it's symmetric, there's no drag. I also plot experimental data points. This set of experimental data points is for the case with the laminar boundary layer on the cylinder walls. We see that our potential flow prediction is pretty good until a little before the top, then the pressure flattens out. This is because the flow separates, and we get a complicated flow with a wake. At a certain range of Reynolds numbers, this actually becomes unsymmetric and makes a Kármán vortex street. This experimental data set is when there's a turbulent boundary layer on the cylinder walls. We see that our potential flow prediction is much better, though it deviates slightly. It has the same shape until roughly about 130 degrees. That's because this turbulent boundary layer separates much later along the wall. It's interesting that there's a 0 Cp around 30 degrees or so for any of these cases. This is where the pressure exactly matches the free stream pressure. Towards the nose of the body, the pressure is higher, and away from that point, the pressure is lower. Now I introduce something called the method of images. This is a really fun and useful technique, which I'll illustrate with an example, namely flow into the 2D attachment of a vacuum cleaner. Let's consider a 2D case where air is drawn into the vacuum cleaner through this 2D attachment. So we're taking a slice where the flow is infinite into the page. Here's our standard XY coordinates, and flow gets sucked into this vacuum cleaner from all around. The goal of the vacuum cleaner, of course, is to suck up dirt from the wall. Most of you probably realize that we could model this suction as a sink, but how do we deal with the wall? That's where the method of images comes in. Imagine a mirror image under the wall, where air is being sucked into an imaginary 2D attachment under the wall. We model this flow by two sinks, one for the actual vacuum and one for this image vacuum. Here's our, quote, real sink, and here's our image sink. And since everything's symmetric top and bottom, one of the streamlines has to lie along the x-axis. The streamlines below the x-axis are an exact mirror image of those on the top of the x-axis. By having an image and a real sink, we can think of the x-axis as the wall. We let B be the distance from the wall to either sink. Thus we can model flow into a vacuum cleaner attachment. We show all the details and math in the textbook. Here are the results. The blue curve and the left scale is a non-dimensional speed along the wall, and the green curve is the pressure coefficient with this scale. Cp is defined the same as we defined for the previous problem. Again, the pressure coefficient is symmetric about the y-axis. The axial velocity along the wall is positive up to x equals 0, since the flow is moving to the right, and it's negative for positive x, since the flow is moving to the left. X star is defined as x over b, and we see that at x over b equal -1 or +1, we have the maximum speed. And by our most beloved Bernoulli equation, we also have minimum pressure. I sketched this back in dimensional coordinates, and we're predicting that the maximum speed along the wall occurs when x equal b or x equal -b. This is where we expect to get the most removal of the dirt, since the air is flowing fastest across the wall. The point directly underneath the vacuum attachment is a stagnation point where there's 0 speed. Thus, despite what most people may think, the vacuum cleaner does not do a good job picking up dirt directly below it. It actually does its best cleaning at some distance, which we're predicting is the same as the distance from the attachment to the wall, or b. Can we test this experimentally? I show a short video clip by one of my former students, Chris Smith. He uses the 2D vacuum cleaner attachment and recorded how it picks up sawdust. When he turns it on, you can see that the vacuum does not do a very good job directly under the attachment. But it does a great job in this region of the flow where the speed is near maximum. Thank you for watching this video. Please subscribe to my YouTube channel for more videos.